Hi, I'm Ben-Yaakov. This presentation is entitled Modeling and Control of Pwm Converters. This is a recording of a part one of a three-part presentation delivered at Texas A&M University to a class of graduate students of the EE department. I'd like to thank Professor Prasad and Jetty for inviting me to share this knowledge with the students of the course Switching Power Supplies. The subject of these three meetings is modeling and control of PWM converters. Let me start with sort of a short motivation here. And I'm showing here a buck converter. This is a synchronous buck with two transistors. This is the inductor, and this is the output section. Normally, this is a commercial unit here, a controller. We like to operate it in, of course, closed loop. And for the purpose of keeping, say, the output voltage constant. So what we need here is to make sure that if there is a voltage change at the input, and if there is a load change at the output, we want the voltage at the output to stay sort of constant and not sort of jump all over the place. This could actually harm components. Like, for example, if you have a microprocessor here, and if the voltage goes up too much, it will damage it. And certainly, you don't want it to oscillate at the output. So this is a feedback system that you have to design. For that, we need to sense the output. We also sense the current, in fact, we'll talk about it. And then you need some phase compensation to make sure that the system is stable and also responsive in a quick way to a change in command. So this is the purpose of what I'm going to talk about in these three lectures, is how to design a system like that. Now, obviously, you can say, okay, we got all these already made. Well, they are made, but you do, first of all, have to understand how they operate, and then most of them do require extra design steps, especially if you are changing like the output. You want it to be a different, you don't want it 2.5, you want it 7 volts. Then you have to know what to do here in order for the system to operate properly. So here's the outline, very short here. This bold part is what we're going to do today, and that is the introduction, average concept, average modeling of PWM converters, and then simulation, average-based simulation, and we'll wrap up with small signal responses that we need for the design. I'll explain this in due course, of course. So what is the problem we are addressing here? We have a system. This is again a buck converter. Here we have a diode rather than a transistor. And we're sensing the output. Here we're sensing the current. We generate a PWM signal to the gate. And this is the control. So our purpose is to design the control part of this system. For that, we have two issues here. Number one, we have to somehow describe this system in a mathematical way that we can handle transfer functions and other expressions. Secondly, we do need some control design rules of how to design a stable system like that, okay? So what we are going to do is, first of all, to handle the issue of how to model this part here so that we can handle it and we can get the responses that are absolutely needed in order to design the control. So this is the first step. The second step, we're going to show how the combination of these can be used to design a stable system according to a given specific set of specifications. So the approach that I'm going to show you is sort of a little bit different from what you've seen in some places. And that is, I'm going to use what I might call user-friendly averaging model, and then use this model to build a simulation setup to get all the responses that I need, and then to develop a control laws that are based on the results of these simulations, that I can use the results of the simulation to actually do the design of the control. And then, of course, to test and see how this control behaves. All this I hope to be able to show in this three meetings. And today we are going, of course, to start with the basic modeling approach of the power stage. By the way, I'm going to use LT-SPICE. I'll talk it in a minute. I understand that you are used to PSIM. It's a very nice program developed by Dr. Hua Jin. By the way, this company was recently bought by Altair. And it's a very nice program, and it's dedicated to power electronics. It's very nice because it sort of ignores the transitions, and therefore there's no conversion problems and some other issues. But it doesn't handle real devices, so you cannot take into account the parameters of a transistors unless you go into the PSIM environment. And, well, nice thing, you can get an evaluation version, which is very, very limited. I'm going to show especially the LT-SPICE version of a SPICE. Now, let me say a few words about SPICE. SPICE was developed by Lawrence Nagel actually in Berkeley in 1973. It was made public domain. And this is why many companies, PSPICE based, LT-SPICE, and then many other companies are using the same engine, the computational engine of SPICE, which is pretty much the same as was developed in 1973. And you can do a lot of things, including AC analysis, which you cannot do in PSIM. In PSIM, what you can do, you can inject a signal and see how it propagates through the output, and then sort of accumulate all these injections into a graph that show you transfer of amplitude and phase. Here, it's a different approach. We're talking about small signal linearization around an operating point, and I'm going, of course, to explain all this so that you'll be able to handle it. I highly recommend that you'll get familiar, because this is now a walking horse, and it is used a lot in industry and in the design environment. Very handy. And the great thing about it, that the full version is free, and it has many features, and it's absolutely free. Well, it's of course part of analog devices advertisement, because they like to push their devices, and therefore it has many of their units in it, but then it has many other companies' units, and you can import units or models from other. So I'm going to base most of the stuff that I'm going to show on LT-SPICE. Okay, so let's go into the nitty-gritty here, and I'm starting with the concept of average. Now, we're talking about one cycle average. One cycle average means that if I have a signal like this, then I'm averaging it over one period, and then take the average value, and this is the value that I'm working. That is, I want to get rid of all the fine details of the switching, and then just talk about the average value. And to do that, you have to take the integral here, of course, divided by the period, and then you get, in this case, it'll be like the duty cycle times the maximum value, because this is the ratio of the time that you have this signal on. Now, if you have a signal like that, then you can take the average here. And by the way, the area, we call this area of the voltage and time volt second, very important in power electronics. I'll talk about it. And then I have a volt second here, I have a volt second here. And if this voltage is sustained, then I can look at the average behavior of the current, and as a function of the average voltage. The average voltage is this, and this will be the average current going up and down. Now, in steady state, this current should come to the same point. That is, the average voltage okay, has to be 0, because otherwise the system will diverge. It will not converge. The current will go up and up. If this is not 0, then this is not 0, and then it go up. So we know that at steady state, the voltage, the average voltage on an inductor must be 0, or you have to design it such that it will come to 0, okay? So this is a very, very important concept, and I'm just restating it here, that if the voltage, the average voltage over a period is not 0, then the current will sort of run away. And this is, of course, very bad. Of course, during transient, you can have a voltage which is changing slowly, and then the current will also follow it. This is something that, of course, we would like to describe and take care of. But eventually, over a whole period of time, the voltage must be 0 in order for the system to be stable. So let's see how we can apply this simple concept here in, say, in a buck converter. Here is again a buck converter, the switch, the diode, and we know what is the transfer function, the duty cycle, etc. But now let's look at it from a different angle. And that is, if I look at the voltage here, here is what I see. Whenever the switch is on, I see a high voltage. Whenever it's off, I see the diode. I assume it's 0 volt. So I see this waveform, and this is one period of time. And if this is one period of time, the average is D times V in. This is V in, and this is the duty cycle here, because this is the D is the ratio of the time it is on. And if at steady state, the voltage across the inductor is 0, then this value, V in D on, which is the average voltage here, has to be equal to here, to this voltage, because the difference has to be 0. And from this, we get V out over V in is D on. Okay, so this is one way to use this concept for steady state transfer function. Now you say, okay, that's simple, we know that. Okay, well, look at this. This is much more complicated. This is a SEPIC converter. By the way, anyone knows what is the advantage of a SEPIC converter? Because it is like a boost, a buck and a boost in a sense, then actually it's a boost and a buck boost. Then you can get a voltage which is higher or lower than the input. Okay, very important. And it is at the same polarity. In the buck boost, you have a reverse polarity, which is not so convenient. Not always you need a negative voltage. So number one, you have a voltage which goes up and down around the input, which is very nice. If you have a 12-volt battery, then sometimes the voltage is higher than 12 volt when you're charging it, and then it goes below 12 volt. And if you need exactly 12 volt, then at one time you have to have a gain. And then if not, if it's below 12 volt, if it's below 12 volt, you need to boost it up. And if it is higher, then you have to lower the voltage. So this is one thing. Another very important thing is that if you have a shorted output, it will not harm the unit because of the capacitor. In other converters, for example, in a buck converter, if you short here, then eventually this current will go up and up and up because this turns on, keeps turning on, and it'll burn out. So these are the two very important advantages of the SEPIC. Okay, but let's go back to our point here, and that is how the hell do I find the transfer function of this thing? Well, of course, you can start write the nodes and branches here and the matrix, etc. But let's see how we can do it very quickly by applying the idea that the voltage across the inductor is 0. And here it is. Here is V in average because the input voltage. So here it must be also V in because the difference is 0. Here the voltage is 0 because average. Because here it's 0. How could it be 0? Because sometimes it's plus, sometimes it's minus. So it's, you know, the average is 0, but we don't worry about the plus minus, just the average. Okay. So we know here is 0, here is V in, so the voltage on the capacitor is V in. Here it is. Okay, so we know a lot about the circuit already, steady state. And then what we do, we look at this point and we say, okay, the voltage at this point, when the transistor is off, is V out plus this voltage in. So it's V out plus V in, because there is V in here. Here it is. This is the voltage at this point. The average of which is times D off, because this is the time that you see the voltage. Otherwise, D on, you see it 0. So this is the basic equation. You open it, and then you know the average voltage here is equal to V in. Here it is. Okay? And you get the V out to V in is D on over D off. Okay? So you can see that this is a very powerful thing here, this average voltage on an inductor, and I'll show you that's in other connections too. Okay? So this is a very important concept, and here I am leaving it for you to work out the transfer function of a Chuck converter, very similar, also actually built on buck boost, 2 stages, also can have a gain larger than 1, smaller than 1, but as it turns out, the output voltage is negative here, okay? So in many cases, it's not very convenient unless you need a negative voltage. Okay, so now we're coming to the issue of DCM. Up to now, I talked about, all what I talked was CCM. In DCM, situation is getting a little bit more complex because the averaging is not that simple, and I'll talk about it a little bit later. And we get into DCM when either the inductance is becoming smaller, or if the current is getting lower and lower, the load current is getting lower. And you can figure out what is the equation of the transfer function for a buck, etc. I'm not going to fiddle with it because I'm going to show you that we can handle this by simulation and get whatever we need from the simulation. So you really don't have to wrestle with all these equations. Now, don't misunderstanding. I'm not belittling analytical expression, derivations, etc. I'm just saying that in many cases, for the practical engineer or for getting some work done of design, etc., you really don't have to go through all these details because we have powerful simulation tool that will do the same thing. And I'll again go back to it back because this is a very important point, I think. Okay, now I'm going into a little bit more deeper into the issue of simulation. And if we look at the basic PWM converters, buck boost, and the derivative of which, for example, flyback is just a derivative of the buck boost, and forward and half bridge and are actually buck converters, full bridge. So these are the basic one. If we look here, we see that all share the same basic unit: inductor, switch, diode. I mean, including the inductor because it's very important. We'll see it later. And the difference is just the orientation. That is here, this is the input, A is the input, and here A is ground, and here is A is actually the output, okay? It doesn't say here, it should be A. So this means that once I know how to model this thing, it's valid for all PWM converters. That's the point. And so this is the basic unit, the basic cell, but the diode is actually working as a switch also, so I can describe it as a switch. But in DCM, you might say there is a third position here when there's no current in the inductor. ECEN means that there is a period in which there is no current through the inductor. So this is the basic model. And now what I'm trying to do is the following. I'm saying, okay, I got this unit here. I'm interested in average values. I don't want to see the details. I don't want to bother with all these switches and all this jumping and on and off. I just want to see a smooth waveform here and here and here, which is describing the behavior of the system. For the behavior of the system, you don't need the fine detail of how the switch is on and off. So I'm looking here, I see here, I see the inductor current at A. I'm going to keep as far as much as I can this labeling of A, B, and C. A, we see the inductor current. B is when the switch is on, we see during D on the current. Here it is. Only during D on we see the current. And at C, we see the rest of the time the current. Here it is. Okay? So we see here it's the average of a waveform like this is just going through the middle point. Okay? It's triangular, so it's the middle point. I'm showing that there is a sort of a transient here, so growing up. So I'm looking at the average here, average here, average here. It's a one cycle averaging. Said that obviously for B, and since the average current of the inductor is going here at the midpoint, so it's actually this area divided by the period, which is actually D on times the inductor current. So what's coming here is D on times the inductor current. And what is coming here is the same way, it will be the inductor current times D off, that is the rest of the time. So that this can be emulated by three current sources. One is the inductor current, one is the inductor current times D on, and one is the inductor current times D off. So this is the basic concept. The question is, where the hell do I get the inductor current, which is needed for the definition of these sources, okay? And here what I'm doing, I'm going to impose on the inductor the average current, okay? I'm imposing the average current, and when I'm imposing it, I'll get the average, I'm imposing the average voltage on it, sorry, and I'll get the average current. Now, obviously, in steady state, it will be, average voltage will be zero, not necessarily the current, because you can have a current circulating when the voltage is zero, okay? If V is zero, the I dt is zero, but the current itself can circulate. So by putting the average voltage on the inductor, this is the actual voltage on the inductor, and this is the average voltage on the inductor. I'm getting, this is the real current of the inductor, but I'm worried about the average, which is a function of the average voltage. So what is the average voltage on the inductor? It is the voltage during this time plus the voltage during this time. This time is A to B, this is time A to C, this is during D on, and this is during D off, or T on and T off, and this is the average current. Now I'm showing you something which is like formal to understand the concept. We are not going to do that. We are going even to simplify it even more, but just we have to understand what is behind what we are doing, and what is behind is that we are finding the current coming out of these three ports, and we are imposing the average voltage on the inductor, and we're getting the average current, which is needed here to define these sources. So here is the model. These are the sources. Here is the voltage, which is a dependent source. Here is the expression for it. I'm drawing it like this, but actually we are talking about current source. In a current source, if you are interested in what's going on here, it's not important where it is connected to. It's a current source, so it's pushing the current to B, so you can draw it any way you wish this side here. So let's see how we implement it in a buck converter. And I'm talking now the formal approach. Again, I'm going to simplify. And what will be the formal approach? I have here A, B, and C. A is where the inductor, and it is connected here to the output. So here's the inductor. C is connected to ground, and B is this point here when the switching is the D on. And the average is, we can see it's V out over V in, and this is according to this expression, and that's it. But we really don't have to be that formal. Once we understand it, once we understand what's behind it, we can very quickly come up with the model. And here it is. I'm looking at this, and I understand that first of all, I have to find what is the average voltage on the inductor. Fine. Here it's already V out, so let's not worry about it. It's an average voltage. It's not pulsating. Here it is pulsating. And the waveform, we've seen it before, is when the switch is on is V in, and when it is off is 0, and the duty cycle is D. So therefore, this voltage here, the average voltage here, is just V in times D on. And if I am interested to find out how much current is required from the input, this will be D on. This is the time the transistor is on, the ratio of the time transistor is on times the inductor current. So the expression for this is IL times D on, and that's it. That's the end of it. So I got the model, okay? What I'm going to do with it, we'll see it in a minute. Boost. Well, here I have the inductor. V in, don't have to touch it. What do we see here? During off time, we see the output. So D off over times V out is the average voltage here. What is the current that is going into the load? It is during, again, T off, and this is the current times the time ratio, which is D off. So this is IL D off. Very simple. And finally, I'm going to show it for buck boost. 0 here. What is the voltage, the average voltage here? Well, on the one hand, during D on, we see V in times D on. This is the volt second, or the ratio of V in on this side. During off, we see V out. So the average voltage here is V in D on plus D off V out. That's it. What is the current that is going to the output? Well, it is the inductor current times the time that this branch is open, which is D off. So therefore, it's IL D off. How much current is consumed here? This is during D on times the current of the inductor. Here it is. That's it. Good. If we want, we can add some parasitics. For example, we take into account the diode in a buck converter. We take into account the ESR, and this will be then implemented and used when we're going to manipulate this model and use it. This is sort of a modified version with the diode and taking into account for a buck converter, the RDS-on taking it in. It's not exactly accurate because here we have average current, and what is passing through the RDS-on is actually RMS and not the average. But as we'll see, for practical purpose, that's pretty good. Now comes the following question. We have expressions like this. We're going to simulate it. IL is a variable, an electrical parameter that the simulator recognizes. D on is now, it looks like a number, but in practice, when you run a simulation, this could come out of the control unit. So it can change with time. And it's not a parameter. It's not a fixed parameter. You cannot define it in param and say, okay, I want this, because this has to be online running and adjusting itself to whatever is required, either by excitation or by the fact that it is an output of the control unit. So the trick we do is the following. For the current of the inductor, no problem. We can define current of the inductor. That's fine. This dependent source will recognize it. For the dion, we defined a node here, and the voltage of this node is recognized as dion. So now, if I want dion over IL, I have to multiply the voltage here times the current. Now this then can come out of a constant source, modulating source, or out of a control system that produces a voltage which is recognized as dion. So this is the trick we're doing. So let's now get to the detail here and see how we do that. Suppose I have in this case, a boost converter, okay? Here's the input, well, it's on the right side here, because this is actually a buck boost, depending how you look at it, okay? But here I put the input voltage, this is the inductor, this is a synchronous boost, okay? 2 transistors, and here's the output. Now, what I'm doing, I'm translating it into, this is empty spice. So let's start with the inductor. We have V in on one side, and then we have a voltage here, the average of which is the output voltage times D off, because this dion is this transistor in a boost, and so that this is D off time, okay, D off ratio, okay? So here it is. This is a dependent source, behavioral source, defined as D off, the voltage of D off, of the node D off, and out. Here I'm defining a node which is D off by a dependent source, which is defined as 1 minus dion. Dion is a parameter that I'm going to change. So this is not the voltage here. This is a parameter that I'm going to change. So at this stage, this is a parameter. So it's a number, okay? Here's the voltage, but this is the number. And this is again a voltage, and this is a number. And I'm here using the voltage of D off, and here I'm using the voltage of D off 2. So this is then the average voltage on the inductor, and the current that is going to the output is the, as we have seen before, is the voltage of the inductor times D off. Here it is. This belongs to this, and this belongs to this. Okay, and this is left as it is, and here it is. And then when I run it, and what I did here, this is a parameter run. I sweep over D on. This is a parameter now. It's not a variable. And what I see is a typical transfer function of a boost converter. It's 1 over D off, 1 over the minus D on. And I've just picked up 2 numbers. The input voltage 25 volts. So 25 over the D, this D is like the number milli, okay, milli D. And you see that the simulation gives us this number. I calculated here and here. It's excellent. It's very, very good. Okay. Now I'm going to complicate things a little bit and talk about linearization and small signal. And this is what we are after. This is the important stuff. A transfer function for this is nice, very important, but that's part of the story. For the dynamics, for the control design, we need small signal. So let me sort of focus here on the issue of what is small signal, and how then can we get the small signal in sort of a switching unit like a PWM, which is non-linear, and it's not trivial how to get the AC of it, the small signal of it. So first of all, I like to emphasize what I mean by small duty cycle, okay? Now, we understand duty cycle is the time that we have the switch is on, okay? Now, suppose the voltage which is causing the duty cycle is changing, then you have a duty cycle which is kind of changing too. It's smaller, larger, etc. Okay? Now, if imagine that this is an oscilloscope, and you put a trigger at the beginning here, so you see all these pulses at the beginning of this trigger, but the ending will be different. It will be sort of jumping all over the place. This is the small signal duty cycle, okay? This is the deviation of the duty cycle from the steady state or operating point, or the point that you are sort of freezing the system, that you look around this point. So this is the meaning of the small signal duty cycle. So how do we get the small signal system, and how do we handle it? And I'm going to show you here, just to go very quickly over it, the application note, Texas Instrument, and it's dealing exactly with this issue of voltage mode boost converter, small signal control loop analysis. Okay, and what are they doing? They develop, in fact, they did not develop, they copied from somewhere the transfer function. And what is this transfer function? It's the small changes in the output as a function of the small duty cycle. So they've copied it. And then they define all the parameters. And then they manipulate it. And then they go and from the parameters, they draw it. And then they use this graph to, to design the control. So in the approach that I'm going to show you, what I'm doing, I'm going to jump over all this part here. Just jump over it. And to get directly from here to here, okay? Or more accurately, to here, because this is what we want. This is the bottom line that we need. Now, again, I'm not belittling the equations, and they are important for finding like principles and behaviors, etc. But for the design, we then go on and look at the numbers and do something with the expressions when the numbers are indent. And this is exactly what simulation does. Simulation is not an approximate. This is a numerical calculation of what? Of this equation. That is, the simulator is actually solving this equation numerically. We don't see it, we don't bother with it, and we just get the result. Okay, so this is the approach I'm going to show you here, without again saying that forget about mathematics, so analytical deviation. That's absolutely not my intention, but what I'm going to show you is how to do design in a more practical way. And this is the objective here of this presentation. So let's move forward and talk about the meaning of linearization, okay? Now, if I have one variable function, y is a function of x, it's nonlinear. Now, what is linearization? It is the derivative at the given point that you are interested in. We call it the operating point of the converter, say it's around 5-volt output. And you take the derivative, the slope is constant, and then you assume that this is a linear system. This was not linear, and now this stands for small signal. I'm not going to stick to it. I'm a little bit not that formal, but here, this means that this is small signal, this is small signal, and this is a constant. Here, It was some nonlinear function. Okay, so this is what we mean by linearization. But what if this is more than one variable? For example, you have x times y. This is a nonlinear system. What then? What does the linearization mean? Well, what it means is that the partial derivative, the differential, the partial derivative with respect to each one of them times dx. Okay, so if I have something like a dependent source, which has like two variables, that's the voltage of a node and then current of something that I call 3, then the meaning of linearization would be the partial derivative of this, that is taking partial derivative of the function with respect to one variable, another variable, and it could be many variables, okay? Not restricted to 2, it's just an example. So in this case, linearization means that you take this function, take the derivative, time, this is now constant because this is at the operating point. This is the slope with respect to this variable. And this is the slope with respect to this variable. So these are constant, and so this now becomes a linear system because there's no multiplication here anymore. Now, it turns out that SPICE, from the original Berkeley up to today, LT-SPICE and all the other derivatives, is doing it by itself, this linearization. Now, obviously, it cannot take analytical derivation, cannot do exact differentiation here, the partial derivative, so it is doing it numerically. It is changing V out by a delta, changing V in by a delta, looking at the ratio, and this is now defined as the constant of this variable now V in. I mean, of this expression here, which is the constant times V in, one of the variable, and this is the constant here times this variable. So whenever you hit the button of AC analysis in any of the SPICE version, LT-SPICE, P-SPICE, multi-sim, whatever, at the background, this is what is done. It's taking this thing, taking the partial derivative numerically, here it is, finding the constant, the slopes, and then describing the system like this, because if I have here two of values here, this is like two sources in series, here it is. And if this is a voltage, it will be in series. It will be a current, it will be in parallel. So for the case of the buck converter, if we describe it the way we did as the dependent sources, which are nonlinear, here are the definition. If you do a AC analysis, what happens is that this is the circuit that will emerge from this. Now, I think it's important to understand what's going on. But on the other hand, you really don't have to worry about it because it is done automatically at the background. It's part of the AC analysis. So let's see how we can demonstrate it here. So I'm again showing the same boost converter. This is the inductor, the average voltage across the inductor, average current going to the output. This is D on, this is D off. And now I'm going to do AC analysis. So this, by the way, when it's blue, it means it's non-active, okay? So this is now active. I'm doing AC analysis between, and looking at the, between 10 hertz to 10 megahertz, 100 points per decade. Here are the parameters. And lo and behold, that's what we see. This is the transfer function between what? Between a small signal in D on here, because this is the AC source, and a small signal here at the out. This is the key that you have to have in order to design the control of the system. This is something that you have to have, because this is the actually starting point. Without it, you cannot design a control. So what we see here, for example, this is the body plot, of course, coming out of LT-Spice in the AC analysis of the circuit. We see the gain, we see the phase. It's kind of interesting. Here you see the phase is starting from 0, then going hard 90 degree, 180 degree. This looks like a double pole, which it is. And we know that the phase shift should be 180, but then it goes on to more negative, to more lag. And this is because if a boost converter, we'll talk about it later, has what the so-called right half plane 0, which is adding a lag to the phase. So the phase is actually going up to 270, not just 180, as would be the case say, in a buck converter. Buck does not have this phenomenon. Now, if I add a ESR, then it will change the transfer function. Here it is. The ESR is actually adding a real 0, and consequently, a 0 has an advance, okay, a advanced phase, and it is adding 90 degree, so it's sort of canceling out the right half plane 0 lagging, and you get back to 190. So very nice, beautiful. Okay, that's very nice. The nice thing about it is that it's easy. I mean, you didn't do pages and pages and pages of equations and derivations. You just hit the button. Once you know how to model it, you just hit the button, you got the result. Otherwise, it's a lot of work. Okay, so let me just show you the following, that if I have a flyback and I describe it, and again, I'm not going into it in very fine detail. Everything is here. I like you to go over it, understand it. Basically, again, I took this inductor, which is this one here, and put the average voltage across it. Average voltage, as I've said, during on is actually the input voltage times the on, and during off, it's the reflected voltage from the output through the transformer, through the coupled inductor, actually. So this is the inductor. This is the output section. Actually, I've added a diode to take into account the voltage drop here. And this is the definition of D on, and this is the definition of D on, and this is D off one, and this is still CCM. So here is the time domain simulation. The red one is the output voltage in the real, I mean, the switching system. The green is here. Now, in order for us to better see it, I've just shifted this. I've added here, or I actually subtracted 2 volts. So you can see that the switching circuits have here a transit at the beginning, and this is because since the inductor has no current, it starts building up and then it oscillates, very typical of a start without what we call soft start, which I'm not going into, but this is well-known phenomena until the unit stabilizes. Here, we don't have this problem because it's very quickly stabilizes in the AC. There's no switching here. So this is why here immediately it stabilizes. Here, it takes a while. This is a transient phenomena during turn on. But let's look from here on, okay? From here on, you see that this is exactly the same. But the beauty is not this, the beauty is this. This is what you get now, the transfer function between the small signal and the output. This is again the gain, this is the phase. Again, this is a derivative. Flyback is a derivative of buck boost, so therefore it has a right half plane 0. This is why the phase goes to 270 degrees, which makes life very difficult when designing the control. We'll talk about it. Okay, this makes life very important to understand what is going on. So this is the beauty of this approach. Now I'm going to talk about this continuous mode because time is running. Up to now, I discussed only continuous mode. And what I've said is that the current coming off here is the inductor current times the time TO. This is correct if the waveform of the inductor would have been like continuous. Since it is interrupted here, actually I get a smaller signal, I have to correct for it. That is this is T off now is actually something like this. This is T off. This is 1 minus T on, or I should say the period times T on. This is I call it T off prime, is not of interest. What is interest is this timing here, and we need to see the average of the current here. So taking this concept into account, we can do the calculation, or I've done it, and I'm not repeating since we just don't have the time to go through the details. And what is basically done is to calculate the average current in this case. And this is what is important. This is here the expression for D off. Okay, this is, or T off divided by TS is D off. Okay, this is throughout some, geometry with the triangle, the areas, etc. Again, I'm not going into it. It'll take us too much time. So this is the end result. It's an expression. It has to do with the current of the inductor, the value of the inductance, the switching frequency, all we know. Now, this T off is always smaller than this T off prime, okay, shorter. So now I'm invoking a function that all SPICE versions recognize, and this is the minimum function. So now I'm defining D off as the minimum of the two, either 1 minus D on, this will be CCM, or this expression, okay? So when I'm running the simulation, everything is the same, except for not defining D off as 1 minus D on period, but allowing the simulator to decide which is the case here and taking the correct value. So it's very simple. So it's automatically both CCM and DCM. They don't have to switch between them. The simulator is switching. Of course, it corresponds to the operating point. That is, well, in transient, it will go from one to the other, but for small signal, it will first see what is the operating point, then select the D off, and then run the AC analysis. So the big picture here is the following. The model that we have developed at Ben-Gurion University actually is explained here. We have the so-called general switch inductor model. This is the inductor with the two switches. We are generating the inductor current by imposing on it the average voltage. And then we have what we call a duty cycle generator, which could be simple, like it could be, this is the error signal coming from the controller. It could be like a constant times this error signal. I'll show it later. It could be more complicated with the D off, which is dependent on the discontinuous mode. And it could be even more complicated if it is a peak current mode or valley current mode or whatever. And then the duty cycle that is translating this information into the duty cycle is becoming, it's another expression. As long as you can write an expression, you can do the average simulation. So let's have a look here. In the case of a buck converter, this is the buck converter. Inductor, average voltage on it. I defined it now in A, B, and C. The average voltage is the voltage here and here. So this is A, B. I've now labeled it A, B, and C like the actual model, the formal model. It's not necessary, but this is the way it's done here. This is the average current coming to the output. This is the current going to the input. D on is the steady state is the parameter. Then I have AC signal, and D off is defined here. This is this expression here. Okay, it's an expression. It's the current of the inductor and everything else, and the value of this is a parameter. This is the value of the inductance, the period, etc. This is exactly this expression here. So this is the expression for the D off. The D off is the minimum between this and 1 minus VD on, which is for the CCM. I've stepped here the output resistance. And as you know, in a system with a fixed duty cycle, if the resistance, if the load resistance is increasing, then you eventually will go into DCM, and you can see it very nicely here. This is CCM with a constant duty cycle, the output is 5 volt. And as it goes to a higher load, then the voltage goes up, and according to the discontinuous mode situation, this comes out like, you know, very simple. But the real important and very, very pivotal to design, control design, is this transfer function. And what we see here is when the load is low and it is in CCM, this is a transfer function of the buck converter. As I've said, again, it's a second order system. Phase goes to 180, but in this case, due to the ESR that I've added, there is a 0. So this 0 brings back the phase to 90 degrees. We sometimes use this, and we'll see later on, for control. But if the load is 60 ohm, the system now went into DCM, transfer function changed. It's like a first order system. We don't see the second order Q type, resonant type behavior. This is because the system is like more like a current source. Each cycle, the inductor is charged and discharged. So this is like a constant current to the output, which is an RC, and this is the first order system. So we see it very, very nicely here. And this is, again, extremely useful in the design of the control.